Welcome back to Statistics. The real heart of inferential statistics lies in estimating unknown population parameters like population means or population proportions. So, for instance, I might be interested in knowing the true average height of all 20 to 29-year-old US males. But the fact is, I probably just don't have access to all the data I would need in order to really calculate that mean. After all, to do that, I would need to have the height of every 20 to 29-year-old US male before I could calculate the true population mean. But we often have access to sample data, and sample means can be used to estimate those population means. So now we're going to talk about our first real inferential statistics technique. We're going to be estimating population means based on sample data. And the key idea here is going to be the idea of a confidence interval for a mean. This will give me both an estimate for the true mean, a margin of error for that estimate, and a confidence level that attaches to that estimate. So let's take a look. So, estimating mu, introducing confidence intervals. So, the idea is we're trying to estimate a population mean mu. So, that describes the average value of some variable, like height for instance, over an entire population. The fact is that average value, that population average, mu, is generally unknown simply because we don't have access to all the data. But as I mentioned, we usually do have access to sample data, and from that we can get a sample mean from that sample. So the idea is going to be to use the sample mean x bar to estimate the true mean mu. We know that x bar is an unbiased estimator of mu, which means that if you looked at all possible x bar values and threw them all into a histogram, the center of that sampling distribution of x bar would be the true population mean mu. The sampling distribution itself gives us an idea of the quality of that estimate on average. So, for instance, we would know through the spread or standard deviation of the sampling distribution how much the x bar values would vary from sample to sample. But often we want to know more than just what's true on average. For a particular x bar that we're looking at, we'd like to know, how close to the mean is it? And that's going to vary from x bar to x bar. Most of them, as shown by the sampling distribution here, are going to be fairly close to the mean, but there will occasionally be x bar values that are out in the tails of the sampling distribution and that are therefore going to be far away, relatively speaking, from the true mean. So, what can we do here? Well, the idea we're going to pursue is to attach a margin of error to our sample mean in a way so that most of the time, for instance, maybe 95% of the time, for 95% of all x bars, the true mean is within the margin of error. So here I'm just going to add a margin of error to our sample mean x bar. So I've indicated that by this thickened line that extends a certain amount out to the left and that same amount out to the right of x bar. That amount that we use for the margin of error will be denoted by m, and again it goes both below and above the x bar value to form our confidence interval. So if we look at x bar minus the margin of error up to x bar plus the margin of error, we get a range of values. And what we're interested in is the likelihood that the true mean mu falls within that interval of values between x bar minus m and x bar plus m. Depending on where x bar actually lands in the sampling distribution, the true mean may indeed fall within that confidence interval, as I'm indicating here with the green colors. Or, in certain cases, if x bar is out in the tails far enough, it may be the case that the true mean does not fall in the confidence interval. And I'm indicating that here by coloring the confidence interval red. But the idea is going to be that we choose the margin of error so that most of the time, in fact, a prescribed percentage of the time, the true mean does, in fact, fall within the confidence interval. And again, you're seeing that here as I color the confidence interval green. So a confidence interval for estimating mu is an interval of the form x bar plus or minus a margin of error, which I'm denoting here by m, and that interval is denoted this way as just the interval from x bar minus m to x bar plus m. And again, m here represents the margin of error for the confidence interval. So the question becomes, how do we find this margin of error m? Well, that's related to a second idea called the confidence level for the confidence interval. The confidence level for a margin of error m is the fraction of all x bars from the sampling distribution that have the property that the true mean value mu, the true population mean mu, lies inside the confidence interval from x bar minus m up to x bar plus m. So the confidence level of a margin of error is that fraction of the time where the true mean lies within the confidence interval. We should note here that there's a simple way to tell whether the true mean lies within the confidence interval. That's going to happen just in case the distance between x bar and the true mean is less than the margin of error m. So here you see the red values of mu are examples where the distance between mu and x bar is greater than the margin of error. And in those cases, mu will not lie inside the confidence interval. But if the distance between mu and x bar is less than the margin of error, as indicated in green here, then mu will be in the confidence interval. So given a prescribed confidence level C, we can calculate the associated margin of error m, and we can then put together the confidence interval that will be our estimate. So let's take a look at an example. Suppose that height varies normally in a certain population. The mean height is unknown, but to estimate it, we're going to take an SRS of n equal 25 individuals from the population and compute the sample mean. Suppose we find that the sample mean is 67.72 inches. Let's find the margin of error m for a confidence interval with a confidence level of C equal 90%. We can assume that the standard deviation of height in this population is sigma equal 2.5 inches. So we need to find a margin of error m such that 90% of all x bars in the sampling distribution lie within distance m of the true mean mu. Note that these X bars would in fact constitute the middle 90% of the sampling distribution. The sampling distribution of X bar is normal. Why is that? It's because the population distribution was given to be normal in this example. The mean of the sampling distribution is unknown, but we do know the standard deviation. It's just the standard deviation in the population, which is 2.5, divided by the square root of the sample size. So that turns out to be 0.5. So how are we going to find this margin of error so that 90% of all X bars lie within that distance of the true mean? Well, it's helpful to first ask how many standard deviations are needed to span the middle 90% of a normal distribution. So let's ask that question. How many standard deviations do we need to span the middle 90% of a normal distribution? Well, when we're talking about how many standard deviations, we're talking about z-scores. And when we're talking about z-scores, we know that we're talking about the standard normal distribution. So I'm really looking for the span that gives me the middle 90% of a standard normal distribution. We've seen how to do these problems. It turns out that that middle 90% extends from 1.6449 on the right-hand side down to negative 1.6449 on the left-hand side. I'm going to denote that value by z star. So z star is 1.6449 for that middle 90%. If you were looking for a different middle percentage, you would get a different z star. We're going to call those z star values critical values. So we need 1.6449 standard deviations above and below the mean to span the middle 90%. This is called a critical value, as I mentioned, for 90% confidence. So that tells me how many standard deviations I need, and from that I can get the margin of error, because we know that the sampling distribution has a standard deviation of 0.5. So we need 1.6449 of those standard deviations for our margin of error. That's 1.6449 times 0.5, and that turns out to be 0.82245. The units here would be inches because the units of standard deviation are inches. So once the margin of error is found, finding the confidence interval is easy. It's just your sample mean plus or minus the margin of error. So our sample mean was 67.72, so we have 67.72 plus or minus 0.82245. That turns out to be the interval from 66.9 up to 68.54. So this tells us that we're 90% confident that the true mean height mu in this population is between 66.9 inches and 68.54 inches, where I've rounded those values to 2 decimal places. So in summary, a level C confidence interval for a mean takes the form x bar plus or minus m, where m is our margin of error. It's computed by taking that critical value, z star, and multiplying it by the standard deviation of x bar. And you get that critical value just by looking at the bounds of the middle C percentage of the standard normal distribution. I want to point out before we finish that in order to do this, we needed to know the population standard deviation sigma. in order to get off the ground here. We didn't really need to know mu. In fact, the whole point of this exercise is to estimate mu. But in this technique, we do need to know the population standard deviation, sigma, in order to compute the margin of error. So there we have it, our first introduction to inferential statistics in the form of these confidence intervals. We'll continue to discuss them and do some more examples in our next video. In the meantime, if you have questions, let me know. And as always, stay safe, and I will see you next time.